In this video, we're going to talk about complex exponentiation of numbers with base other than e. And first to see, before I explain all this, why we don't normally see things like 2 to the I, 2 to the 3i plus 4, or 8 to the I, and we usually see things more like e to the I, e to the some constant times I. Let's take a look at why it's convenient to have e as a base. So we know from just Taylor series expansion is one way to prove this. E to the I times some constant is cosine of that constant plus I times sine of that constant. So for instance, if we have e to the I pi over 2, we know that that corresponds to just a 90-degree counterclockwise rotation if you sub in here. And that's convenient because if we plug in e to the I pi over 2, we see we rotate by exactly that argument of pi over 2. And that's not the case with other bases. So that's why e is super special. This is really the big idea right here. So without an extra just scaling constant in front of it, this could be 2 e to the I constant, then we'd be extending some magnitude 2 and then rotating by that constant. But this is really special here. So if we look at one way to see what 2 to the I is, let's first review some log rules. First, e to the natural log of something equals that something. And that's because if e to the 3 is around 20, natural log of 20 we're defining as 3. It's just unwrapping that. So this exclamation mark equals is my shorthand for definition. So now we see if we take e to the ln of 20, that's the same thing as e to the 3 because we defined that. And e to the 3 we know is 20. So that's where we get this rule here. The next rule is if we have the natural log of something to a power, we can bring that power out front as a coefficient. And then the third rule, exponentiation just maps addition to multiplication in this way. So here if we take 2 to the I, we can use this first rule, star, as adding some complexity, e to the natural log of 2 to the I. So we know that's the same thing. And this is helpful because now we can see we have e as the base with I, and now some argument here, which we know from Taylor series expansion, this argument is going to be the amount of radians we're rotating. So we can see that it's not convenient to have 2 to the I because that means a magnitude of 1, rotation of not 1, but natural log of 2 radians. So here we can see 2 to the I plotted here on this unit circle is 39.7 degree rotation, whereas if we have e to the I, it's a single radian rotation, which is nice and clean. And 1 radian is about 57 degrees. And then the conversion between radians and degrees is have the scale factor, 180 degrees per pi radians. Now let's look at something a little more complicated, like 2 to this 3i plus 4. Well, if we use this third log rule here, we can change addition into multiplication in this way. Now this 16 just means we're scaling our magnitude from the origin by 16 rather than 1. And because of this other first log rule that we used previously, we can take this other term, 2 to the 3i, and expand it as e to the ln 2 to the 3i. Now we can take this exponent out front, 16 times e to the 3i times natural log of 2. And if we simplify, just multiply the natural log of 2 by 3, because natural log of 2 is just a number, it's not a fancy function. We have 16 e to the I times 2.08, which is the natural log of 2 times 3 is 2.08. And if we convert that to degrees, we see that that is 119 degrees. And that also happens to be 16 times 8 to the I, if this were a magnitude of 16 away from the origin. Here it's plotted as a magnitude of 1. And just as a quick aside, that's, you know that this is 2 to the 3i is also 8 to the I in this way. So conversely, if we were to have a nice base of e for this exponent, we could quickly find that it's e to the 4, which is just some number close to 55, with a rotation of 3 radians, which is about 170 degrees. All right, and that's why it's convenient to have e as a base.